So this is E658 lecture 36. The last time around we saw that when you want to make a single unit current cell, what you want to do is the following. M1, M2, this is the switching pair, and this goes to the load resistance, and as we understand, the output goes to other switching sources, and this is B and B bar, and this is M3, M4. M1 is the basic current source, and the size of this is simply determined by matching considerations. Once you have frozen the architecture and the segmentation, for example, this is just the size of M1 is just determined by matching. M2 is the cascode device which you want to keep also in saturation. The functions of M2 are twofold, as we discussed. One is of course to enhance the DC output impedance of M1, so that the current doesn't change when the drain voltage of M2 changes. Another important function of M2 is the following. We know that M1, because it's dependent on matching, M1 is likely to be a large device, okay, because you want the current sources to match very well to hit a given resolution. Now if M1 is a large device, then the parasitic capacitance here is likely also to be large, correct? So and we saw the last time around that any parasitic capacitance at the switch node, if I, for example, did not have M2 and directly connected M1 to the switch, the current switch, then during the crossing of B and B bar, the inevitable glitch that would occur here would result in a large displacement current in the parasitic capacitance at this node. So one strategy is definitely to try and minimize the glitch. Another thing is of course to minimize the parasitic capacitance. So if you did both, then you're doing as well as you can. So M2 basically isolates this node, okay, with a large capacitance from this node. So the equivalent parasitic capacitance at the drain of M2 is the parasitic capacitance due to the depletion capacitance between the drain and the substrate of M2, and the gate capacitances and the depletion capacitances from these sources to the bulk. So that is the sum total of all the parasitic capacitance here, which ought to be minimized. So what you want to do as a designer is minimize the size of M2 so that the drain parasitic of M2 is reduced, and minimize the sizes of M3 and M4 so that CGS of M3 and M4 are reduced. And what else? You want to make sure that, as far as, this is the best you can do as far as the parasitic capacitance at the source of M3 and M4 are concerned. What can you comment about the waveforms B and B bar? As a designer, what would you strive to do? You want to make sure that M3 and M4 are never off at the same time. We saw what bad things can happen when both M3 and M4 are off at the same time. In that case, what will happen is that this poor current source will try to pull current out of that node, which basically means that all the charge that is there on the parasitic capacitance keep going down, and suddenly when one of them comes off, all that parasitic capacitance will discharge back into that node, causing a large glitch. What I would do as a designer would be to start with M3, M4 being minimum size, okay, because that's the smallest you can make them, and make sure that you have enough. I mean, please note that you want to make sure that all the transistors M3, M4, M1, M2 are always in saturation. So you choose the minimum possible size for M3, M4 and M2 if you meet the headroom requirement. All right. How do you figure out if you are meeting the headroom requirement? What is the least voltage that can, I mean, when is one of these guys likely to go into triode? When this voltage goes to the absolute minimum. And what is the absolute minimum voltage that this guy can take? VDD minus. Please note that this current is not just one single cell, many cells are coming together. So VDD minus, so let me call that I full scale, okay, single ended, times R is the lowest potential that can go to. Under those circumstances, you must make sure that all the transistors are in saturation. I mean, the other side, if this is in saturation, automatically the other side will all be in saturation because no current is flowing through the other leg. If all the currents are switched this way, this is the lowest that the drain of M4 can go to, okay. And as I said, B and B bar need not be full rail signals. So all that you need is enough. I mean, you have to basically apply a differential voltage large enough between the gates of M3 and M4, which is enough to switch the pair completely. So far so good. Let's see what other stuff can bite you when you're making a current steering DAC. Once you've made these cells, you have to put many of these things together and make the entire thing, correct? And when you're putting many cells together, it's obviously not possible to compress all of them into zero space. They will occupy some space, which means that you have to route all these logics. I mean, please note that each of these switching signals are dependent on the input digital code in some fashion, correct? So the input digital code has to be processed, and the resulting, the enable waveform for this particular cell has to be routed from somewhere, correct? So there are several ways in which you can arrange these transistor cells. The simplest thing, these current cells. So the ways in which you can arrange these cells motivate our next discussion. Let's see. So let's say you're trying to make a thermometer DAC, right? The simplest thing I can think of are simply current cell 1, current cell 2, current cell 3, current cell 4, blah blah blah. Current cell, let me take the example of a 6-bit converter, so it's like 1 all the way to 63. I mean, this box here represents all the transistors that I've drawn, and these are the two outputs, and then I join them all up. So one straightforward way in which one can think of to lay these cells out is basically, this is the lower line here represents the ground line. Then you propagate all the bias lines like this, for example, and perhaps you take the input digital code, okay, the 6 bits, right, and then generate the thermometer code. The input is logic, right? As a simple minded fellow, the first thing I would try is simply feed it on put the decoder, on the right or to the left, or if I was a little more careful, I'd probably put it in the center so that it's halfway between the two. Seems reasonable, right? There's no rocket science. This is what I would do. Let's see. I mean, if this works, then you're all set, right? You just move on to the next topic. If we figure out if there is some problem, then we have to figure out what the problem is and fix it. So what do you think the problem is? I forgot the all important clock. This is the DAC clock, correct? And the 6-bit logic signal and the digital input signal has to be synchronous with the clock. So what this means is that if the clock is doing this, the data will only change at whatever. The input data is supposed to change only at the edges of the clock. So since anyway the changes in the data occur at the rising edge of the clock, as a simpleton, what I would simply do would be, okay, not bother with routing the clock anywhere because I don't need the clock. I just need to generate the enabled signals of B and the B bar, and I mean at a pinch I can even say just give me B, I'll generate B bar locally. I don't need to generate B bar somewhere and then propagate it all the way across. So in other words, the least number of wires I can think of, that need to propagate down from the right to the left are basically 63 because each one needs one enabled signal. An alternate way of doing it is to actually propagate the 6-bit digital word to all the cells and locally generate the thermometer code, corresponding to this cell. The enable signal must be a function of the 6 bits, correct? So you can do a logic minimization and then go and figure out what logic you need to put in here. That will typically blow up the area of the cell, okay? Because it's the logic is not trivial logic, because if you write the truth table for when cell 1 should be on, the complexity of the logic first of all depends on which cell you are at, and it's likely to require a few gates in the best case, which basically means that each of these cells keep becoming bigger and bigger. Once these cells become bigger and bigger, what happens to the transistors inside? Please note that you want the current source here, the bottom M1 here and the M1 here to be very well matched. If you want well matched transistors, will you put them 2 miles apart or will you put them next to each other? You want to put them next to each other. One could argue that I could take the 6-bit word, and propagate it along the entire array and locally generate the logic which goes and enables the DAC. An argument against that is that the digital logic that I need to use to generate this thing is likely to blow up the area of the cell, which means that matching will now be, compromised. So it makes, so a reasonable thing to do is to generate the 63 lines somewhere and propagate the 63 lines. Of course, now you are stuck with the problem of propagating these 63 lines. Okay, that's one of your problems. So the 6-bit data is all synchronous with the clock, correct? So can you comment on what will happen to the edges of these decoded outputs when you pass through a decoder? You're taking this 6-bit logic, right, 6-bit digital word, and you're generating 63 lines through some combinational logic. And if I look at the transitions, ideally if all gates inside the decoder were delayless, then as soon as the data changes, the outputs must all change instantaneously. In other words, the delay is 0. Not only that, whenever there is a transition in any one of those 63 output lines, the transitions will all line up in time, correct? Because the transitions all occur at the same time, because the delay in all the logic gates is 0. In practice, all logic gates will have delay, and since some outputs pass through different types of gates inside, it is perfectly, in fact I would be very, very surprised if the output transitions at the decoder all line up in time. So with finite delay, there is going to be skews at the edges of the output of the decoder. Not only that, the moment you propagate those lines all the way across the array, you have an additional problem, which is, do you think the output will get, the decoder outputs will take a long time to reach 1 or to reach 63? They will take a long time to reach 1, they will take a short time to reach 63. In other words, even though you assert the command signal saying this cell go on at the same time, even if you did that, which we know is not possible because of logic delays inside the decoder, we know that due to the way the current cells are laid out, some of these cells will turn on at, between the time the enable signal is asserted at the decoder and the time it takes for the cell to actually turn on, the delay will be dependent on the location of the cell in the array. Another practical issue is whenever you have combinational logic, it is very likely that for some specific changes in the input code, the digital code, there will be glitches in the output. Okay, so you would expect, for example, when the data changes from some code 7 to code 9, for example, you probably expected some control line to do, say, this. Okay, ideally, in practice, there will be finite rise time, and depending on the data sequence and the way the combinational logic is designed inside, it is not unlikely that you end up with a sequence which does this. This depends on different paths how data propagates during inside the combinational logic. So if you are working in a digital environment, you are only looking at here, and if everything is edge triggered, for example, you are looking here and probably looking there, so you don't care. This is essentially a level triggered system, right? So when the input is is high, the current source tries to do this. When the input is low, the current source tries to get switched to the opposite direction. So a waveform like this is what? Is it acceptable or is it not acceptable to go and drive the current sources? It's not acceptable. So doing this directly has problems like delay, dependent on data, delay dependent on location in the array. So a unit I pushed out by this guy is not equivalent to a unit I pushed out by this guy, which is not equivalent to a unit I pushed out by that guy. Correct? So what does that mean? This is nonlinearity. And as we discussed, glitches from the combinational logic in the decode. So can somebody propose a solution to this? So one clean way of avoiding all these glitch problems is to simply propagate a clock line along the array, and what happens? The clock, for example, so if you put a master slave type latch at the input of each current cell, then this, depending on the how you trigger it, let's say this is rising edge triggered, you can basically, even though the combinational logic has got a whole bunch of glitches, because you are only sampling at one point in time, you can eliminate all glitches. So this loosely is called syncing the data with the clock at every current cell. And not only that, let's assume for the time being that this clock line delay is 0. Okay, that means the transition of the clock, the rising edge of the clock here versus the 63rd, let's assume that they all happen at the same time. It's not true in practice, but let's assume that that's the case. In which case, what happens? The command to switch these current sources all happens at the same time because it is synchronized with the clock edge. So the solution is basically locally. So syncing with the clock locally ensures that the command given to the switching pair is synced across all current cells with the global clock. but there still remains one problem. What is that problem? I mean, there is definitely bound to be clock skew from cell 1 to cell 63, and this is going to get worse and worse. For what? If you have more current sources, this is going to become a pain. Not only that, even if the resolution of the DAC increases, you can expect that the cells will become bigger. Okay. And one argument you can take is that I will send the clock from the middle and then split it. I don't send it from left to right. I will bring the clock in the center and split it into two branches, one going left, one going right. So now the delay is reduced by a factor of 2. So one thing to do is definitely say, okay, I don't want to have this clock and all this other stuff. What I'm going to do is go and design the combinational logic in the decoder so carefully that glitches don't happen. But even if you do that, you will never be able to ensure that the transitions are all aligned. And even if you do, and the delays will all be dependent on the previous state of the combinational logic as well as the next state, correct? So there is always, there is clearly dependent on the previous stuff and the present stuff. So the delay, you can never make it to be independent of state, okay? And even if all those lined up at that point, the moment you route it, you will find that there is still some delay. Definitely not synchronizing the enable signals locally with a clock is just something which will never work. So one idea is say, so these are all the current cells. The problem is now the decoder is here. So clearly if you draw a line from here to here and here to here, there are two different lines. So how will you make them equal? One is to put this here and to put this here, correct? No, this is a valid approach, right? So now if you draw a line from here to here or here to here, the two of them are just as long. This is definitely an idea which will get rid of. This is like dipole moment, right? If it is so far away, correct? It only goes as 1 over r square rather than 1 over r. This is the same argument, isn't it? So, some poor soul has to drive all this capacitance if you run long wires, right? So the idea, I guess, is therefore to. So the bottom line is that you definitely need a clock to sync. Is the necessity for having a syncing with a clock clear? Okay, and based on the skill of the designer and experience, you can figure out a whole bunch of tricks by which you can put this here and put that there. There's, as you can see, there is no big mathematical equation to be solved and minimized to get the optimal. It's all, a lot of it is just simply common sense, right? So syncing with the clock is definitely something that you want to do. Okay, so is there something else you can do with the layout? One problem with putting things in a line like this is that if the number of cells become larger and larger, this will run from here to Timbuktu, right? So it's clearly it's not doesn't seem as attractive as it seems with 4 current sources as with when you see say a 10-bit thermometer DAC, in which case this will be 1024 current sources and it becomes a bloody nightmare. So anything that you think you'd be able to do? So as you can see, the stuff therefore is to not lay things out in a straight line like this, but as a rectangular array, right, or a square array. So in other words, let me take an example of a 6-bit converter again. So 6 bits is 3 sources, which is like 64. So 8 aside. Okay. So 1, 2, okay. So blah blah blah. Now these sources have to be controlled by a 6-bit data word, and each one of these current sources has got a unique row column address. So one way of reaching a particular cell is to, you have just a 3-bit decoder. So 3 bits, let's say these are the LSBs and these are the MSBs. So this is the column decoder. This is the row decoder. And it's not just as straightforward as simply, selecting the row and going directly to the cell. You know that if you're trying to build a thermometer DAC, let's see, if a certain cell, so let's say this is row I and column K, what should you do? You need some simple logic to figure out. Please note that if this guy should be on only when, you just can't, this current cell in row I and column K cannot be on, it cannot be only dependent on row I and column K. It must also be looking at the row I minus 1. If row I minus 1 is 1, see how does the thermometer stuff work? So the MSB 3 bits will determine how many of these rows are on, correct? And so let's say the code was say 15. Then what should happen? The first row should be on fully, and only the first 7 in the second row should be on, correct? So the enable signal B should be some function of row of I minus 1, I and K. And you take B and then generate the B bar locally. And it's important to generate this B bar properly, because if there's an overlap between B and B bar, that's when you're okay. If at any time during the entire cycle, if you find that tail current node is dipping, then you're in for trouble. And you should propagate the clock. I guess you either do it this way or this way. A small thing that I want to mention here. So, how do you model skew it as the clock propagates from left to right? Why is there delay, first of all? It's RC, correct? So this is R, this is C, RC, blah blah blah. Have I discussed this before? The total delay is roughly, very very crudely you would think that it is N times R times N times C. It in fact, the fact that it is distributed actually makes it smaller. It's actually 1/3 RC. That's the time it takes. That's what you will get if you go and do the it is a distributed transmission line and go and do the math. But the key point I want to bring out is the delay from here. Let's call this TD. For the same wire, if I bring in the clock in the middle, what do you think is the delay from here to here? If I yank this reaches there at a time TD later. If I yank this, how fast do you think it will reach the left end? TD by 4. Why?
Resistance is half.
The capacitance is halved, the resistance is also halved. Okay? So the delay you're doing better by factor of 4. The DAC current sources are now sitting in a nice clean square array. So you have the row column decoding logic, and when you have a segmented DAC, the thermometer DAC is basically realized like this. The binary section is anyway small, so you can either do that also this way, or you just put them in a straight line. Okay, and so this is how it happens. Now there is in really high precision converters there is an additional problem, and that relates to the fact that this is not going to be a small thing, right? This is going to occupy some space, and all process variables like threshold and oxide thickness and things like that all have some kind of, I mean, they are not absolutely constant across the die, right? So the zeroth order approximation is that everything is constant, Vt is constant across the entire area of the current sources. The first order approximation is what? There is a linear variation in the x direction, there is a linear variation, I mean, so ideally you would expect everything to be a flat surface. The first order approximation is that it is not flat, it is a plane but is tilted in some orbit direction. What that means is that the current sources here and the current sources here are not the same thing. So can you suggest a smart idea which will fix this problem? Do you know do you understand the problem? The problem is that if I had a transistor here and generated VGS, some bias voltage, if I apply the same bias voltage to a nominally identical transistor here, the current will be different because the Vt is slightly different. Please note that this is a systematic variation. I am not talking here about random mismatch. So if I did this for 10 transistors in this area, the currents of them all, the average will be much higher than the average of currents of 10 transistors, say somewhere here and there. One idea is to basically generate bias locally. Another idea is to simply realize that the problem is coming because of the spatial extent of the current source array. So what I can do is, let's say I break up my current sources into 4 identical current sources which are 1/4 the size, lay them out as 4 individual DACs like this, and just add the outputs. So this is an example. Now since the areas of each of these guys is very small, is much smaller than this chap, the spatial variation of current sources will now be much smaller, correct? Because the slope, if you assume that the slope of the plane is the same, the way if you go only 1/4 halfway across, the change is divided by a factor of 2, correct? The variation from between these two is 1/2 the variation between this and there is a whole bunch of now theory about how you can randomly assign current sources at different places and average out this whole thing. I am not going to get into the details, but all that I want to emphasize is that there is a problem with gradients of oxide thickness and threshold across the current source array, and in principle you can, one way of fixing the problem to some degree is to split this into 4 smaller DACs. Since each of these DACs is smaller, it will occupy a smaller amount of space. You put 4 together and then add them up, okay? And for example, if some current source was I, for example, you split it into 4 equal current sources of I by 4, okay, 1/4 and 1/4. The other you have another current source, you split it into 4 things like this, and what do you see? If the distribution of Vt, for example, was a plane, correct? Then the average of the shaded rectangles is exactly the average of the unshaded rectangles, correct? Because this is compensated out by this chap and this variation is compensated out by this. So in other words, the centroid of this is this, and so is the centroid of these guys. So this is a common trick played by a lot of DACs. So to give you an example, a photograph. Yeah. So this, for example, is one chip that we did here.